Good afternoon. I would like to talk about the paramagnetic nature of electronic structure and spin excitations in the strontium rutenate. I did this research with my supervisor Jan Kunesh and also with Jiří Chalopka, Atsushi Hariki, and Hiroshi Shinaka. So the strontium rutenate is layered crystal with weakly bounded SrRu2O6 planes, where the ruthenium atoms create honeycomb structure, and they have partially filled 4D shells by free electrons. T2G orbitals are split by trigonal crystal field into A1G and E-pi-G orbitals. It is known as antiferromagnetic insulator with easy axis, with magnetization easy axis along the z-axis and non-negligible spin orbit coupling. So all these properties lead to some very interesting physical phenomena. Many of them have already been explained. The first one is rather high Nel temperature that was measured to something more than 560 kelvins. Then the absence of Curie-wise behavior above the Nel temperature in the uniform susceptibility was observed. And this was explained by the presence of short-range order in the material. Neutron powder diffraction revealed a reduced local magnetic moment from theoretically predicted free Bohr magnetons. They measured only 1.4 of Bohr magneton. Atsushi Hariki and his colleagues were, however, able to explain and reproduce this reduction by proper accounting for the overlaps of one-year orbitals. And then there is a question that so far does not have unique answer. And this is the question of the nature of paramagnetic electronic structure. So there are two candidates, Mott and covalent insulator. To give some analogy to these two candidates, let's imagine a hydrogen molecule with tunable Coulomb interaction. When the Coulomb interaction is high, we will have two localized electrons on the atoms that would correspond to the limiting case of the Mott insulator. And when we decrease the Coulomb interaction, we get a molecular orbital, and this would correspond to covalent insulator. In our material, it's caused by specific hopping structure of the electrons on the ruthenium atoms. And in the limit case, the electrons would hop only within the hexagon and would not be able to hop between hexagons. So the difference is well visible in the density of state, while in the Mott insulating phase there is a sizable charge gap. When we look at the covalent insulating phase, bonding and anti-bonding molecular peaks are created, and in the half filling, which is our case, the Fermi energy falls between these two orbitals, and this should stabilize the covalent insulator. On the other hand, there is the tendency to form high-spin Mott insulating state, and this is again maximal at the half filling. So we have two phases competing with each other, and we can go from one phase to another by tuning of temperature and the size of the Hund's coupling. When we have low values of the Hund's coupling, we are in the covalent insulating phase, and as we increase the Hund's coupling, we get to Mott insulator. So the motivation to this research was a paper of Hakuto Suzuki and his colleagues, where they, as first, measured 4D materials by resonant inelastic spectroscopy. The measured spectra can be seen here. So we can see at the low energies, we can see the magnon dispersion. And when we go to higher energies, there is a disperseless structure corresponding to the transition between the states with spin 1/2 and spin 3/2. And then there is an electron-hole continuum. In this work, they explained the high Nel temperature by the existence of the large spin gap in the magnon spectra. And they argued that the spin gap stabilizes the magnetic order up to high temperatures. And they also captured the magnon spectra by spin 3/2 Heisenberg model extended by single ion anisotropy. So the model can be seen here. And thus they concluded that since the magnon spectra are well described by the strong coupling model, it could suggest that strontium ruthenate could be Mott insulator. So we were wondering whether it's possible to use the description of magnetic excitations to determine if the material is covalent or Mott insulator. In order to answer this question, we calculated dynamic spin susceptibility, and our first goal was to reproduce the data that are marked as red dots. And here in this figure we can also nicely see the spin gap. And to calculate the spin susceptibility, we used DFT plus DMFT approach, followed by solving of Bethe-Salpeter equation. And to get some better insight to the validity of the strong coupling model, we employed the strong coupling expansion and exact diagonalization of the Hubbard model on a single bond. So when we look at the band structure of the strontium ruthenate, we can see that T2G orbitals are well separated from the EG orbitals, and they're also separated from the P orbitals from oxygen atoms. So for our calculations, we used T2G only effective model. And since also in the paper of Hakuto Suzuki, they showed that the interaction between layers is very weak and does not affect the magnon spectra too much. We only worked with 2D planes. To describe the interaction on the single side, we used Slater-Kanamori interaction. So, as first, we looked at the effect of spin-orbit coupling. Spin-orbit coupling causes single ion anisotropy that leads to the existence of magnetization ESI axis. The single ion anisotropy we could directly see in the eigenvalues of Anderson impurity model. So here we can see that the ground state is split into two doublets by the energy roughly 7 millieV, and this is the single ion anisotropy. We further looked at the effect of spin-orbit coupling to magnon spectra. So we calculated magnon spectra with and without spin-orbit coupling included. On the left-hand side, we can see gapless magnon spectra. This corresponds to the calculation where the spin-orbit coupling was switched off, and when we switch it on, the spin gap opened, as we would expect. Further, we compared our calculations with experimental data. Experimental data are gray dots. And when we look at the figure B, we can see by naked eye that our calculations reproduce quite well the experiment. We were also able to reproduce this disperseless structure corresponding to the transition between S3 and S1 states. Further, we estimated nearest neighbor exchange interaction by strong coupling expansion and also the size of the spin gap. In the formula for the exchange interaction, we used the parameters that we used in the DMFT calculation. And when we look at the values of exchange interaction and compare it with the experiment, we can see that they fit quite well, as well as the spin gap. We also determined the exchange interaction from the Magnum bandwidth, and it gave us something like 61 millieV. But the spin gap was larger, it was 45 millieV. So now we can see that calculations reproduced the experiment quite well. When we look at the parameters for which we calculated the spectra, we can see that we took the value of the Hund's coupling that is on the covalent insulating side of the space diagram. So this doesn't mean that the strontium ruthenate is covalent insulator, but it is worth it to maybe look at more values of the Hund's coupling and look how Magnum changes when we go to Mott insulating phase. So I've chosen 3 values of the Hund's coupling. One was on the covalent insulating side, and 2 were on the Mott insulating side of the phase diagram. And we can see that there is no qualitative difference in the Magnum spectra. So how can we distinguish between covalent and Mott insulator? Well, we can look at the spectral functions, again for these 2 values of the Hund's coupling, and we can look at the spectral functions in the paramagnetic phase and antiferromagnetic phase. The paramagnetic phase we got in the way that we forced spin symmetry in the self-energies in the DMFT calculation. So in the antiferromagnetic phase, we can see basically spin polarized bands for both values of Hund's coupling. However, when we look at the paramagnetic phase, there is a huge difference in spectral function. Actually, we already seen it in density of states a few slides ago. So in the case of Mott insulator, there is sizable charge gap caused by the peak in the imaginary part of the self-energy around the Fermi level. On the other hand, when we look at the covalent insulator, the intensity of the spectral function is significant around the Fermi level, and this is caused by the fact that imaginary part of the spectral function is vanishing around the Fermi energy. So this is something what we can build on. And we were also interested in temperature dependence of the imaginary part of self-energies in the paramagnetic solutions, again for 2 values of the Hund's coupling. When we look at high temperatures, we can see that the imaginary part of the self-energy behaves quite similarly. So there is this peak around the Fermi energy. When we go to lower energies, lower temperatures in the Mott insulator, the peaks get sharper. However, when we look at the covalent insulator, below some critical temperature that we will call crossover temperature between covalent and Mott insulator, and we will mark it T star, we can see that the self-energy starts to behave completely different, and it has Fermi liquid-like behavior. Another quantity we can look at, and it can be quite interesting to look at it, is uniform susceptibility. We were again interested in paramagnetic solutions, so for every calculated temperature, we forced paramagnetic solution. So what we would expect is Curie-Weiss behavior, and it's shown by the gray line. And again, the same story. At high temperatures, the behavior is similar, and when we go to lower temperatures, Mott insulator roughly follows the Curie-Weiss law. But below the T star, which we determined to 580 kelvins, the uniform susceptibility of the covalent insulator drops. So far I introduced 2 temperature scales. Now I will introduce one more. So the first one is T star, crossover temperature between covalent and Mott insulator. And in the comparison with other 2 temperature scales, it has very strong dependence on the Hund's coupling. Then there is experimental ordering temperature that can be determined by the spin gap, and this is the ordering temperature of the long-range order, which was determined or measured to something more than 560 kelvins. And then there is the temperature that gives us the onset of antiferromagnetic correlations in the material. So when the short-range order appears, and this is reflected in the magnum bandwidth, and can be also determined by our DMFT calculation as an ordering temperature, and we determined it to roughly 1,500 kelvin. So as I mentioned, the physics of covalent insulator can be observed in the paramagnetic phase, and so this would mean that the T star, the crossover temperature, would have to be higher than the temperature theta, than the temperature of the onset of antiferromagnetic correlations. However, in the range of the Hund's coupling that we were analyzing, and particularly for the smaller value of the Hund's coupling, we get that the experimental ordering temperature is smaller than T star, and T star is substantially smaller than theta. So this would mean that the covalent insulator remains hidden behind antiferromagnetic correlations. So to conclude, we calculated dynamic susceptibility and were able to reproduce the energy of the spin gap and the bandwidth of the magnum measured by resonant inelastic spectroscopy. It is not suitable to use the study of antiferromagnetic ordered phase to determine whether the strontium ruthenate is covalent or Mott insulator. And our calculations showed that the crossover temperature T star is smaller than the onset of antiferromagnetic correlations theta, and thus the covalent insulating state remains hidden. So this is all from me. Thank you for your attention, and also thank you for organizers for having me here.